Okay, so now we've actually seen various solutions to the Friedmann equation, and we know how it behaves for different values of the equation of state. We also, and that I haven't talked about, but this is stuff that Max tells you about, provided that we know the values at the current epoch, we can actually basically solve the Friedmann equation and solve for the entire evolution of the universe, right? So let's just write it out, and we'll talk much more about these things along the course, and in particular Max, of course, about these cosmological parameters. But let's just say that we know roughly that the total value of omega is equal to 1 in our universe. We roughly know that the current contribution of matter is about 30% to that. About 0.05 is in baryonic, meaning normal matter. About 10 to the minus 4 currently is in the form of radiation, so that's quite little. And the remaining 0.7 is in the form of dark energy. But of course that is not universally true at all times, right? That's just a snapshot at the current point. So if we actually plot it with the energy density as a function of scale factor, well, let's say that A equal to 1, that's today. We have dark energy here that really is just a constant, at least that's what we assume it is. Matter is a little bit less, so that might be this curve. But of course, it's quite easy to see that if we go back in time, very quickly we reach a point here where matter becomes more important than dark energy. Likewise, if you proceed into the future, eventually matter becomes completely negligible and it's just a dark energy dominated universe. Now, even though radiation at the present epoch is down here somewhere and dynamically completely unimportant, of course, the fact that it goes as a to the minus 4 means that eventually, as you go back in time, it crosses. And it's also quite easy to calculate when it happens, right? Because we know that this scales as a to the minus 3, this scales as a to the minus 4. So you can just take the current ratio here, and then you'll find that 10 to the minus 4 divided by 0.3, that's approximately 3 times 10 to the minus 4, sort of. And that means when you get back to an A of 10 to the minus 4 or a few times 10 to the minus 4, before that point the universe is entirely radiation dominated. That means if you go very far back in time, you can neglect all components other than relativistic particles. Then we have an intermediate range here where the universe is matter dominated. And then we have a final asymptotic future here where the universe is lambda dominated. So really you're always almost in a situation where you have one component dominating the other two. And that means you can actually use these very simple analytic solutions to the Friedmann equation for most of the evolution of the universe, which is quite neat. Another thing we'll see later in the course when we do structure formation is that actually structure formation in a universe can work only during matter domination. So all the stuff that you see in the universe today, galaxies and clusters of galaxies and so on, they were all formed in this epoch here. Because once dark energy takes over, then structure formation stops. So whatever galaxies and clusters have formed, of course, remain, but we're not going to form any new larger clusters of galaxies. So we'll see that later. It's quite intriguing, though, that our universe needs an epoch of matter domination, because otherwise we wouldn't be here to worry about it. So we'll see later how that actually comes about. Now, once we're through this, we essentially know all there is to know. Right? That's classical, normal Friedmann-Robertson-Walker cosmology. I've said all there is to say about it. There is nothing more. You can solve the Friedmann equation, that's it. But of course, that's very, very, very far from the truth. So first of all, of course, the universe is not exactly homogeneous and isotropic. That's stuff to look at. But the other thing is that in all cases, when we do all these calculations, we always assume that whatever particles are around are always around. So if you have baryons, they are going to be there at all times. They just dilute and do whatever as a function of time when the universe expands, but the number is conserved. But that's not exactly true necessarily. Actually, it depends a lot on whether whatever physics produces or destroys particles is in equilibrium or not. So that's the next topic that we're going to go into, and that's something that presumably you haven't really seen before, the study of non-equilibrium physics in an expanding universe. Now, before we get to that, I just wanted to spend a little bit of time on another thing which is important for Max's part of the course, namely the notion of distances in an expanding universe. Because, for example, if you measure the Hubble parameter by looking at distant, very bright objects like supernovae, of course you have to know the distance to the object. The question is, what do I even mean by distance here? That's maybe not so obvious, as you'll see in a minute. At least we have to worry about our definition of distances. So that's just a very final little thing before we get to the non-equilibrium physics. So distances in cosmology. So let's go back and look at the Friedmann-Robertson-Walker metric. Which looks like this, okay? So what happens, for example, to a photon? So I imagine I have a bright object that it shines light. This light propagates towards me, the observer. Then we know that because they are photons, they are massless particles, they propagate on null geodesics. That's exactly what happens, right? They propagate at the speed of light. And that means that we can always use the fact that ds squared is equal to 0 for a photon. Then, of course, in my coordinate system, it's easiest if I choose the origin of the coordinate system as either the source or the observer, because then whatever photon path I'm looking at is going to be a radial curve. So that means that this term becomes 0. So altogether, I can write out this null geodesic condition in this form, which is going to be exploitable in just a minute. Now let's look at some object, and we're sitting down here as the observer. Of course, there's some coordinate distance, radial distance between us and the source. That's a conserved quantity, right? It's only the physical distance that changes, not the coordinate distance. That remains fixed at all times. And we can get the coordinate distance by simply integrating the metric along this direction. That's a completely trivial thing, right? But of course, I could also rewrite this by using the condition I have over there and write it as an integral over time from emission to observation. So that would also give me the radial distance. And now you see that this coordinate distance actually depends a lot on how the scale factor evolves. And that means it becomes different in different universes. I can also convert this into a physical, actual proper distance, as it's called. And that would be corresponding to S in our Friedmann-Robertson-Walker metric. Well, S by definition, of course, is the scale factor at the current epoch, the one where we want the proper distance measured, times the coordinate distance. And that I could also write as this integral here. So that would give me the proper distance currently to an object that emitted light at some previous epoch. Of course, it's not equivalent, mind you, to the proper distance at the emission time. The proper distance at the emission time is different by the ratio of the scale factors, because the coordinate distance is the same, but the scale factor at the emission point, of course, is different because we're looking at an earlier point in the evolution of the universe. So that's really important to bear in mind. Now, of course, we can calculate, given that we now know simple solutions to the Friedmann equation, we can actually calculate what is the proper distance. So just to give you an example, let's imagine that we are in this situation where you have some bright object that emits light in the super early universe. So we approximate the emission time just to be 0. And then we observe it over here at t0. Then the question is, what is the current distance to that point? That is what is known as the horizon distance, because it's the furthest we can receive information from. So it's our, if you want, causal horizon. So that's given by this integral here, where I just take the lower limit to be 0. And that we can calculate. So just for simplicity, we know that the universe, as we go back in time, was matter and radiation dominated. So those are the two interesting cases. And in a matter-dominated universe, where A is proportional to t to the 2/3, we actually find that this is equal to t 3 times the current time. So intriguingly enough, the current distance to the furthest point with which we can have causal contact is actually 3 times the velocity of light times the age of the universe, right? So it looks like stuff is propagating at superluminal speed. Of course, that's not the case. The case is that the universe expands while the photons are moving, and that's why the current distance is larger than the age of the universe times the speed of light. There's nothing non-causal about it whatsoever. For radiation domination, we find a very, very similar result. We just find 2 times the age of the universe, right? So it's again the same thing. Stuff appears superluminal even though it isn't. Now this proper distance is of course a well-defined and meaningful quantity, but it's not an observable quantity, right? It's something you can calculate. You can infer the current distance to that point which emitted the light, but it's not really related to any simple observable. So instead, let's just turn to how one would actually go about measuring distances normally in astronomy. So the way that one normally measures a distance in astronomy is through what is known as luminosity distance, right? So you measure some star or galaxy or whatever, then you assume you know the absolute luminosity of that object, then you sit over here as the observer, and you measure an apparent luminosity. And these are just simply related through Gauss's law, where d is the distance, right? So you basically just smear out the entire flux coming out of the source over the sphere with area 4 pi d squared. There's nothing more to it. So this holds true, for example, of course, in normal static Euclidean space, but it does not hold true in an expanding and curved universe. But what we can do is to say, okay, let's assume that this relation, I mean, there's always some relation between little l and capital L, for sure. And let's call the quantity that we need in order to relate these two, let's call that the luminosity distance. But in that case, the luminosity distance, of course, is not presumably equal to the proper distance. At least we don't know if it's equal unless we do the actual calculation of what the luminosity distance is. Okay, so more generally speaking, how would we go about it? Well, first of all, of course, one would need indeed to relate these two through the area of the surface surrounding the source at the radius equal to the coordinate distance between source and observer, because then you know how much sphere you have to distribute flux lines over. So one would need the area calculation. And how does one calculate the area of a two-sphere in a curved space-time? Well, just briefly go back to simpler times when we just looked at Euclidean geometry, right? And remember, how does one calculate the surface area of a sphere? Well, you take some infinitesimal area here, call it dA. We have a polar coordinate system like this. Then we have a vector pointing to whatever point. Then the angle here is usually called the polar angle. And this length here, that would just be r times d theta. Now, of course, I also need the transverse area here, and this angle we normally call the azimuthal angle. But of course, this is not r times d phi, because it's not an orthonormal coordinate system, right? So this length changes as a function of the polar angle, and we know we need to multiply it with sine of theta. Okay, so once I have this, then it's easy enough to get the area. I just need to integrate over all allowed values on the sphere, which is 0 to pi for d theta, and it's 0 to 2 pi for d phi. And then I get r squared sine theta, like this. And I do the integral, and then I find 4 pi r squared. There's nothing more to it, right? That's it. Okay, so that is no longer generally true. In fact, if you want to generalize this to curved spaces in whatever dimensions you're looking at, the general formula is that some physical volume in n dimensions is equal to the coordinate integral. So that's all the allowed coordinate range. But of course, I want a physical volume, not a coordinate volume. So I need to multiply with something that has to do with the metric. And what I need to multiply with is minus the determinant of the metric tensor, which of course, in our particular case, when we look at the diagonal metric, is nice and simple because it's just multiplying all the diagonal terms of the Friedmann-Robertson-Walker metric. And I have the minus. Remember that I always have a minus sign on the time component and plus signs on all other. And that means this altogether becomes a positive quantity in here, which is good because I have to take a square root. Okay, so if we actually write out the metric, like this, then remember that I'm looking at a spherical surface in 2 dimensions. I'm not after the whole 4-dimensional space-time volume. I'm after a 2-dimensional physical spherical surface. And that should be at a value which is constant in r, and it should be evaluated at a specific time. So dt and dr are equal to 0. So the actual 2D metric I'm worried about, and now I assumed, let's generalize it to curved coordinates, then I get an s kappa squared, and then d omega squared. But then of course remember now that the metric tensor that I'm after in these 2 dimensions, well, that must be one which is a squared s kappa squared, and then a squared s kappa squared, and then this is the normal solid angle element, which means I have to have a sine squared theta here. And now I'm done. Because now all I need is to realize that this is actually exactly the same metric as a normal Euclidean space if I only look at the angular part, because this depends on time and radial coordinate, this depends on time and radial coordinate, but not on angles. And that means it automatically goes outside the integral here. So actually the integral is exactly the same as it is in the Euclidean case. The only thing I need to do to the area is to properly multiply it. So the r squared that enters here becomes different. Everything else is the same. And that means that I don't get 4 pi r squared. In fact, the area of the 2-sphere now becomes, well, almost the same factor of 4 pi, but then I get a squared s kappa squared. So this replaces the little r squared. Now remember, if I was in a static Euclidean space, then a is just equal to 1, and s kappa is just equal to r. So in that case, I do have 4 pi r squared. But this is more general because it takes into account the expansion of the universe and it takes into account the curvature of the universe. Okay, so far so good. So now I know the area that I have to distribute flux lines over. But of course that's not all there is to it, because the flux lines change, unlike the case in static space. And how do they change? Well, so one thing I need, of course, to worry about is the fact that the energy of a photon is proportional to 1 divided by scale factor. That means that as the light propagates, it actually loses energy. But there's one more thing that I have to worry about, and that is, remember, capital L is power, so it's energy per unit time, and little l, of course, is flux per unit, so it's energy through a surface per unit of time. So now let's do a little thought experiment. So let's imagine that over here at the source, some light pulse is emitted, and then a little bit later, some other light pulse is emitted. And let's say that the distance in time between these two is delta TE. Now those two light pulses, they propagate towards the observer, which they hit over here. And at this point, the distance between them is delta T 0. And those two are not identical, because of course the length is stretched, and that includes the physical length between the two photons. And we also know the relation. We know that it must be true that this is the ratio of the scale factors at emission and observing time. So that actually means the amount of energy you receive per unit time goes down by this factor, A0 divided by AE. So altogether, the amount of energy I receive at the observing point is degraded by a factor A squared rather than just A from the energy loss to each photon, because time stretches. So that actually means I can now write this, and then I have the area, which is 4 pi s kappa squared A squared, and then I get this factor squared. This factor I could also, for example, if I wanted, call 1 plus redshift, so then I get 1 plus redshift squared. Then normally, this, of course, remember, is the current value of the scale factor, which we normally put to 1. And if we do that, then we now have the final relation saying that the relation between absolute luminosity and apparent luminosity is given like this. But we also defined this to be L divided by 4 pi dl squared. And that means we now have an expression for dl, the luminosity distance. So here we get luminosity distance equal to 1 plus z times s kappa. And again, check that in the static, not in the static, but in the non-curved universe, this is equal to coordinate distance. And A0 is equal to 1. So in fact, if I neglected this term, I would get exactly the normal proper distance to the object, same as the luminosity distance. But this is no longer true. I get this extra factor of 1 plus z, which I have to take into account. So for example, when Max shows you a Hubble diagram of type 1a supernovae that you can use to measure the Hubble parameter and dark energy and so on, what you're actually measuring is the luminosity distance as a function of redshift. And you use that to infer what the cosmological model is, and you use it to infer the presence of dark energy. So that's one extremely useful distance measure that you can have. It turns out there's one more which is equally useful, because of course there's another way of measuring distance in astronomy. And that other way of measuring distance is called the angular diameter distance. So So the angular diameter distance is based on observations of extended objects. So it's not a single point-like source like a star, for example, or a supernova. It's some extended object like a galaxy, for example. Then we sit down here and we make the observation. And what we observe in this case is the angular extent on the sky of this source that we're looking at. Then, of course, if we know through magic or whatever how big this distance is out here at the source at the source point, then we can infer the distance. So in normal Euclidean space, to first order, this would be L divided by the distance to the object, right? It's very simple. It's also, incidentally, of course, the type of geometric construction that you use for parallax measurements of distance. But in this case, we're not sitting here, we're sitting down here, and we have to infer the distance from the extent of the object. Okay, of course, this is true in Euclidean space and static space, but no longer in an expanding space-time and a curved space-time. So we have to take that into account. But we do the same thing as before. So we basically extend this to be a definition. And then again, presumably this is not equivalent to the proper distance to the object. It's some other distance that we call the angular diameter distance. So let's see how one calculates that. So again, as before, we start from the metric. Like this. But now, of course, it's slightly different from before. So now we're looking at a transverse distance at some specified coordinate distance. So we put the origin here at us, and then we're interested in the distance out here. Now, of course, it's the distance at some specified point in time. So dt is equal to 0. It's also at some specified radial distance. So this is also 0. So we only have the angular part left. And let me just write it out. Like this. Now, of course, I'm always free to rotate my coordinate system such that the little line I need has phi equal to 0. So it just sits along the polar direction. So then I can neglect this term, and then it becomes super simple, right? So the physical length is given by a squared s kappa squared d theta squared. But the physical length I could also call dl squared, right? So that's the actual length of the arrow over there. One thing though, what is the scale factor that I need? Is it the one at the observing time or the emission time? That's really crucial. And of course I must choose the scale factor at the point of emission, because after all I'm looking at the physical distance between two photons emitted here at the emission time, not the observation time. And of course you can easily see that since this is an expanding metric, as time proceeds, that coordinate distance here remains the same, but the physical distance changes. This, of course, is not the same as saying that the physical object changes in size. That remains, right, presumably because it's a bound galaxy. But these two geodesics are dragged apart by the expansion of the universe. So it's important to remember that this is actually the emission scale factor. And now I have everything I need, because now I can actually do my full derivation here. So now I can isolate the theta just like over there, and then I get dl divided by AE s kappa. And that means that the angular diameter distance is the scale factor, times s kappa. Now the scale factor at emission time, of course, is, if I assume, like before, that the scale factor at the present is equal to 1, then I can write this as 1 divided by 1 plus z. So it's smaller, of course, than the scale factor currently is. So then I get s kappa divided by 1 plus z. So remember, the luminosity distance was 1 plus z times s kappa. The angular diameter distance is as s kappa divided by 1 plus z. So this actually has a quite weird implication. If I was to try and draw for you what that looks like, as a function of redshift, then if I take the proper distance, it does something like this. But the luminosity distance increases much faster because of this extra 1 plus z term. For small values of z, it doesn't change, right? Because the 1 dominates. But as soon as z becomes large, then it starts to diverge. And the angular diameter distance also starts out as the same, but then it turns over and it actually starts dropping again. Like this. So this is quite weird. What it means is that once I pass a certain point in redshift, an object would actually start to look bigger on the sky as it becomes more distant. And of course it's this dragging a part of the geodesics that's the culprit here. It's just because the geodesics start close by each other, but then they are dragged apart by the expansion of the universe. And that effect actually gets to dominate over the normal 1 divided by 4 pi r squared term from Gauss's law. So that's quite intriguing. Now, of course, an angular diameter distance is not so easy to measure because it would require us to have what is known as a standard yardstick or a standard ruler, right? We need something of specified physical length. And a typical galaxy doesn't really have that because galaxies evolve over time. They become larger as time proceeds because they merge and absorb other galaxies. So that's not a very good measure. And in fact, it's almost impossible to do this type of measurement. But one thing that turns out to be the case is that there are actually ways of measuring this. And that could be done using either the cosmic microwave background radiation, because there you have hot and cold spots on the sky, and you can measure the distance in angular space between them, and you can actually calculate from first principle the physical distance between them at emission time. So that's extremely neat and extremely useful, and the reasoning you actually use to deduce that the universe has flat geometry from observations of the CMB. You can also use something that Max is also going to talk about, namely baryon acoustic oscillations, to do the same thing but at lower redshift. So in fact, it is possible to use the angular diameter distance for something in cosmology. It is an extremely useful tool. But this concludes what I had to say about, if you want, classical Friedman-Robertson-Walker homogeneous and isotropic cosmology. So now we leave that simple world and then we try and make progress into non-equilibrium physics and deviations eventually from homogeneity and isotropy.